Hello everybody, my name is Koishibekov. I am physics teacher. I am working at NIS of Taras, and today we are going to talk about the law of conservation of momentum. So let's start.
So let's talk about the law of conservation of momentum. We have two learning objectives of the lesson. First one is state the principle of conservation of momentum, and second one is apply the principle of conservation of momentum to solve simple problems including elastic and inelastic interactions between two bodies in one dimension. And also I wanted to show you the lesson objectives. First one is state Newton's three laws of motion. Second one, explain a closed system and the interactions of objects within it. The third one states the principle of conservation of momentum in sentence form. The fourth one, use vectors diagrams to determine the total momentum of the system. And fifth one, calculate the kinetic energy before and after a collision for both perfectly inelastic and almost elastic collision. So first let's start with the real life questions where we can face off the momentum. The question is why mountain climbers use nylon ropes. What do you think? Now let's see the answer. The answer is to increase the stopping time and to reduce the stopping force. The next question is which one is easy to stop, a slow moving bike or a fast moving bike? Of course, it's slow moving bike. The next question is which one is easy to stop, slow moving bike or slow moving car? So the answer is a slow bike. The next one is a true-false question. New cars crumple in accident because engineers decided to use cheaper materials. Is it true or false? What do you think? The answer is false. They were designed to crumple as a way to lengthen the time of the collision and thus decrease the forces felt by the occupants. What sports exhibit examples of momentum? Or in which sports you can face the momentum? So it's pool billiards, bowling, curling, or shuffleboard. Why are engineers interested in momentum? Why we are studying the momentum? The answer is to design safer vehicles. So it's really to save our lives. Could a bee fly fast enough crash into and stop a moving bowling ball? Of course, it depends on the size and speed of the bowling ball. Why in cars uses airbags? We know that the airbags save our lives, but what's the real reason? The answer is airbags increase the time taken for the head's momentum to reach zero, so reduce the forces on it, and they also act as soft cushion and prevent cuts. So now let's talk about the Newton's third law. The Newton's first law, it says that an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So on the picture you see the ball and no forces acted on it, so it will stay at rest how it was before. On the next picture you see the asteroids which is moving, there is no forces acted on it, and so that's why it's just moving as it was before. The Newton's second law, it said that when the resultant force is applied to a body, it produces an acceleration that is directly proportional to the resultant force and in the same direction as the force. So if you look at the pictures, it's very hard to this boy to move this very big sumo guy, and or like in the next picture, it's very hard or you need to effort a lot of force to move the bus which is stuck. The Newton's third law every action has an equal and opposite reaction. So if you look at the pictures, you see the rocket which is going up, and there must be the force to win the gravitational force and go to the space. Or the second picture, when you see the footballers playing, when they hit somebody, they also hurt, and that's why we can say that there is action, there will be also the reaction. Now we are going to see the derivation of the equation of conservation of momentum by Newton's three law. For Newton's second and third law, we know that the action is equal to reaction, and the force 1 is equal to minus force 2. And don't forget about the vector quantities. And then from the Newton's second law, we know that the force is equal to mass times acceleration, and we put it instead of the F. And then the acceleration is equal to delta V over delta T, and if we put it into the equation, we get the m1 times delta V1 over delta T equal to minus m2 delta V2 over delta T. Because the time here is equal, they will cancel, and we get the equation in this form. Then we just open the change in velocity, and we get that the initial momentum will be equal to the final momentum. And at the end, we can say that for a collision occurring between two objects in an isolated system, the total momentum of two objects before the collision is equal to the total momentum of the two objects after the collision. So let's look again at our learning objective of the lesson, which was state the principle of conservation of momentum, which we actually did, and also let's look at the lesson objectives. The lesson objective, the state Newton's free law of motion, which we actually did, and the second one states the principle of conservation of momentum, which we actually did. And now let's continue with the other lesson objectives. So now we are going to work with simulation to state whether the collisions are elastic or inelastic. You need to enter to this simulation by this link to the FED Colorado and work with it. Now let's look at the lesson objective which was left. First, explain a closed system and the interaction of the object within it. So we are going to talk about the closed system and the interactions of the object with this simulation. And also at this simulation we are going to see the vector diagrams to determine the total momentum of the system. Third one, we are going to calculate the kinetic energy before and after a collision for both perfectly inelastic and almost elastic collision. Before using this simulation, I need to tell you that we are going to use the closed system. What does it mean? The closed system when there is no external forces acting on the bodies. It is like the heat energy when the objects collide. There might be the heat, or there is some deformations when they hit together, or it can be the friction when they're moving on something. In this closed system we use the arrows, which is showing with the green arrow like this, and this is the velocities. Why we need this? Because when we are going to show the movement of the objects, the velocity, the direction of the velocity, because it's a vector quantity, it's very important. So now let's work with this simulation. To do that, we need this table, and within this table we are going to analyze the collision. Here we put it is a perfectly elastic collision, and let's see what kind of the values will change at the perfectly elastic collision. Here we need to put at the table, you see that we have the masses 1.2 for two objects, and we have v initial, the velocity initial 1.5 for the first object, and for the second object is minus 1.8. We also have the p initial, the momentum initial for first object is 1.8, and for the second minus 2.16. And also let's look at the kinetic energy, which is very important here. it is 3.29. And now let's look what will happen after the collision. So now let's fill this table. V final for the first object is minus 1.80, for the second object 1.50, and the momentum final for the first object it is minus 2.16, and for the second 1.80. And if you look at the kinetic energy, it doesn't change. So from this example we see that the P final and the P initial is the same, it doesn't change, so we can say that the momentum is conserved. For the kinetic energy we see that it also didn't change, so we can say that it is the kinetic energy conserved. Now let's look at the second table. We need to put these values, we need to change the masses. And the velocities. Now let's fill what we have. We have momentum initial for the first object is 3.12, and for the second is 0. We have the kinetic energy initial, it is 2.03, and let's look what will happen after the collision. So let's write the velocity final for the first object, it is a minus 0.43, for the second object 0.87, and the momentum final for the first object is minus 1.04, for the second object 4.16, and we can see that the momentum initial and the momentum final is the same, so we can say that the momentum is conserved, and we see the kinetic energy initial and the kinetic energy final is the same, they didn't change, so we can say that the kinetic energy also conserved. Let's look at the next table. We need to put the masses and the velocities. We don't have here one velocity, but we have the momentum, initial momentum, and we can calculate the velocity with the equation, and it will be 2.6, and for the second one 0.85. Now let's fill the table. We have the momentum initial for the first object is 11.50, for the second object 3.31, and we see that the kinetic energy initial is 27.86, and let's see what will happen after the collision. The velocity for the first object is changed to 0.03, and the velocity for the second is 3.78. If you look at the momentum for the momentum final for the first object, it's 0.07, and for the second one it is 14.74, and we see that the momentum initial and momentum final doesn't change, and kinetic energy also didn't change, so we can say that the momentum and the kinetic energy is conserved for the perfectly elastic collision. Now let's look at the perfectly inelastic collision. If you look, we have the momentum initial. We are going to write it and fill the table. It is for the first object is 1.80, for the second one is minus 2.16, and we have the kinetic energy, which is 3.29, and let's look what will happen after the collision. Let's write the final velocity for the first object is minus 0.15, and for the second one minus 0.15, and the momentum final for the first object is minus 0.18, and for the second one minus 0.18. And if you look at the kinetic energy for final, it's a 0.03. So we can say that the momentum initial and momentum final is the same, it didn't change, but the kinetic energy is not conserved because it did change. So now let's look at the second table. We have the values of the mass and the initial velocity. Now let's fill the table. We have the momentum initial for the first object is 3.12, and for the second one is 0. We have the kinetic energy, which is equal to 2.03, and let's look what will happen after the collision. Let's fill the table. The velocity final is equal to, for the first object is 0.43, for the second one 0.43. The momentum final is equal to 1.04, and for the second one 2.08. So the momentum, it didn't change, but the kinetic energy final is equal to 0.68. So you see the kinetic initial and kinetic final did change, so the kinetic energy is not conserved. So we can say that in perfectly inelastic collision, the kinetic energy doesn't conserve. So let's return to the lesson objectives. It was explain a closed system and the interactions of the object within it. Use vectors diagrams to determine the total momentum of the system, and calculate the kinetic energy before and after a collision for both perfectly inelastic and almost elastic collision. So we explained about the closed system when there is no external forces acting on the object, and we saw that there was some vector diagrams, the direction of the velocities, and we calculate the kinetic energy before and after a collision and look how they change in perfectly elastic and perfectly inelastic collisions. And now let's continue with the practical work with the pendulum to use the equation of conservation of momentum. With this practical work, we are going to confirm the law of conservation of momentum, and let's see how in real life it actually works.
So this is a practical work which we are going to do. We have two pendulums. I put the plastilin because I want to do the inelastic collision, so they need to join together and go together. I measure the masses of these two pendulums, of these two balls, and then what I am going to do, first here I will take one ball and bring it approximately to the 8 centimeter. It is right here, you can see it's 8 centimeters. Now this ball will go, and you see they stick together and they rise to approximately here. I will do it several times. I will take the average value. Why I am doing this one? Because I need height to calculate the kinetic energy and potential energy, and use the conservation of energy to calculate the initial and the final velocity. So what do you think? Why these balls doesn't rise to the 8 centimeters again when I release it, and it just go?
And after we repeat all of the work again and again for 5 or 6 times, we get the average values, and let's look what was happened. So we get the masses. The mass 1 of the ball was 65.1 gram. The mass 2 is equal to 65.81 gram. The height at which the first pendulum was raised was 7 centimeters. Actually there was 8, but then because the pendulum was in air there was a differences like in 1 centimeters, so we just subtract them. The height of these two objects which they raised together, there was approximately 4.2 centimeters, and of course it's the average. So what we are going to use, we are going to use the conservation of energy. The energy initial and energy final is equal, and we know that energy initial and the final is actually the kinetic and potential energies, and you see the equations. Then the second one, we are going to use the conservation of momentum. Because we are looking for the inelastic collision, we are going to use this equation where the two masses is joined together. So first we are going to calculate the velocity of the object which was falling from the height of 7 centimeter, and using the conservation of energy, you see we just, because the object at first it was at the 7 centimeter height, there was no kinetic energy, but there is only the potential energy, and at the end when it goes down there is no potential energy. All the potential energy will be transferred to the kinetic energy. After we derive the equation, we get the V final is equal to root of square 2 times g times h, and we get the answer 1.17 meter per second. And then using the conservation of momentum equation, we get that the second pendulum was not moving, that's why the momentum of this body was 0, and when we subtract the equation, we get that the velocity of two objects moving together was 0.58 meter per second. And the next one, we again put, using the conservation of energy equation, we write the equation, and then we get that at the bottom there was no potential energy, that's why there is only the kinetic energy. Then it's getting higher, and there is a potential energy and the kinetic energy. So when we subtract, we get the h is equal to v initial square minus v final square over 2g, and this is what we get. We have a height of practical, it was 4.2 centimeters, but from the calculation we get 5.3 centimeter. And there is a question, why the practical results and the calculation are not the same, and what do you think? Of course you are right if you think that there was some energy loss, because we are talking about the inelastic collision, and in real life do something which there is no energy loss is very hard. So that's why some energy gone to the earth by the heat, by the friction, and that's why practical and calculation values is not the same.
So I hope you enjoy my video, so let's see the next time.